so welcome. This is the Arizona Department of Education's webinar called A Look at the New Science Standards. So my name is Rebecca Gorelli. I am the new K-12 Science and STEM Specialist here at the agency, and I'm happy that you have joined us, so thanks for being here. This is the live chat icon, and whenever you see this, this is going to be an opportunity for you to collaborate in the chat box with the other participants. So here's our objectives for today's webinar. The first thing we're going to do is describe the instructional shifts that are represented in our new standards. Then we'll spend a couple minutes talking about the implementation timeline and what that looks like. And finally, we're going to do some work around what is three-dimensional science instruction and what does that actually look like in the classroom. So let's get started with our first objective. To do that, not sure if you had an opportunity to check the materials before you joined us, but I provided this document for you. It's called A New Vision for Science Education, and it was provided by the National Research Council. And it kind of goes through the instructional shifts of what will science education involve less of and what will science education involve more of. So if you haven't had a chance to look at this, I blew it up, made it a little bigger, and hopefully you can take a look at it now. And just spend a minute or two reading over what is on this document, and then when you're ready, go ahead and type an answer to the live chat opportunity in regards to what are 3 to 5 items that resonate with you from this document. Thank you for kicking off the chat box. And yes, we do see things with investigation driven by students' questions. Thank you. All right. Thank you for taking the time to do that. I think it's really exciting when we look at the shifts that are going to be embedded in our new science standards. So let's dive a little deeper as we continue. So real quick, before we move on, here is a word cloud that was generated at a professional development learning experience with high school teachers at Coolidge. And this really is an amazing visual that really just shows the shifts. We're going to move away from rote memorization, worksheets, oversimplification, the pre-planned outcomes, that pre-prescribed kind of scientific method, and we're going to move away and we're going to move into investigations where the students are engaging and modeling and investigating and exploring phenomena with their peers, and it's a really exciting shift. And so just real quick, I wanted to remind you, if you didn't know, or let you know that on our website, if you go to azed.gov, we already have some additional science videos ready. If you are wondering, are there any resources for you to share with your colleagues, or after this webinar, you really want to dive more deeply into the standards, please just go to our website, and there's already a few videos uploaded. So let's move on to the discussion about the implementation timeline. So here is the timeline. This was last year. We started with adopting new standards in fall of 2018. We are currently in year 1 of the transition and implementation plan. And if you look at this document, this year we are supposed to begin implementation of the new standards. And if you go down to the second bullet point, you'll see that AIMS science testing will still continue for this year. For year 2, which is next year, we're going to continue implementation with our new standards. And again, if you're looking at the second bullet point there, AIMS science testing will still happen in the spring of year 2 as well. It's when we get to year 3 that full implementation definitely needs to happen. And this is where the new science assessment is going to occur. And if you take a look where it says 5th grade, 5th graders will now be tested on all of the standards from 3rd, 4th, and 5th grade. 8th grade will be tested on 6th, 7th, and 8th grade standards. And 11th grade is going to be tested on the 9th, 10th, and 11th grade essential standards, which we'll talk about high school standards a little bit later in this webinar. And so before we dive into our new standards, let's just build our background knowledge about how does this all work? How do standards and curriculum and instruction come together to build our science learning experiences? So what I'd like you to do is take a moment and read each of these columns. And when you are ready, we have another live chat opportunity. And what I'm going to ask you to do is try to explain the difference between these 3 items in 9 words or less. All right, even if you haven't had a chance to write in the box yet, that's okay. If you want to, you may. I'm just going to keep this moving. So if we take a look at standards, this is really what the student needs to know and understand. Curriculum are the resources used for teaching and learning, and instruction is used by teachers to teach their students the methods. And one more thing to bring to your attention is that standards are really at the State Board of Education level. They are adopted by the State Board of Education. Curriculum is at the local level, which is decided on by districts and schools. And finally, the instruction is employed by the individual teachers. So again, we have that state level, the local level, and then the individual teacher level. So before we begin to really dive into the standards, we're going to do one more activity where we really think about our new standards versus our old standards. And so our new standards we call the content standards, and our old standards were called performance objectives. So what I'd like you to do is just take a moment and read the information in regards to these two, and then on the next slide we'll dive a little bit deeper. Hopefully you had a chance to read this. I'm going to move on to the next slide. So here is kind of a summary of what you just read. And what I'd like to do this time is to really look at these bullet points and compare them. And so for a live chat opportunity this time, what stands out to you as a big difference between a standard, which is what we now have, versus a performance objective? What are the implications? I see someone said, I feel like they are the exact opposite. Absolutely. And I see we're talking about a smaller scope. A standard is much more open. Performance is more closed. Excellent observation. Thank you. Yeah, so this is really exciting. When we think about standards, bullet point number 2 is my favorite, higher depth of knowledge. Our students are really going to be engaging in science the way scientists do. And what I'm glad we're moving away from is this one and done performance objective where we just sit down with our standards and we check off, hey, we taught that, we taught that, we taught that. That is going to be a major shift for us moving forward with our new standards, and it's going to be very exciting. So let's move on and get into our standards a little bit. So here, what I like to do is just do a comparison side by side of an old performance objective versus a new standard. And I pulled this from 4th grade. This is the concept of energy and magnetism. And if you take a look, I pulled a similar kind of content strand from 4th grade from our new standards on the right. And if we take a look at performance objective number 2, it simply reads, construct series and parallel electric circuits. Well, when I read that, I start to visualize students with materials out on the desk, building different types of circuits and just kind of putting wires together to an energy source, and then kapow, something happens. Yay, the light bulb goes on. And I don't really know if the students are cognizant or understand how the energy actually flows from that energy source through the wires and illuminates that bulb. I'm not exactly sure what they know other than that they can maybe follow a prescripted procedure that says step 1, connect this red wire to the battery. But what I love about our new standards, and if you take a look at the new standard, it's not that the content is very different. It's the approach to how we're asking students to show us their knowledge, to engage in science, and to demonstrate their thinking. And so look at what this standard says. It says develop and use a model that explains how energy moved from place to place through electric circuits. Right then I can see that the word explains is in there. They're going to have to show me and demonstrate their knowledge. And I think this is a very large shift that we're going to see in a lot of old performance objectives and compare them to the new standards, is really that depth of knowledge. So let's go on a little bit more and talk about how are our standards built. Our standards were built using what's called three-dimensional science instruction. And so before we begin, just need to give you a little background about how were these new science standards built. Well, our committee put together, which was of 110 educators, used 2 different research documents. On the left here, you see what's called a framework for science, K-12 science education. And on the right is another research document called Working with Big Ideas of Science Education. And so NGSS, the Next Generation Science Standards, if you're familiar with those, the national standards, were actually built using this framework. What was also interesting is that our standards are use this framework to build them as well. So while we are not an NGSS state, we definitely have some common ground and some components that are similar because we both use the same document to develop the standards. But what is different between the Arizona Science Standards and the NGSS is that Arizona included core ideas or content knowledge from working with big ideas of science education. So we are not an NGSS state, we are a framework-based state, which means we just use the same document as NGSS. So if you would like to learn a little more about these documents, there are free downloads of both of them, and I will send them to you in the follow-up email after the webinar is over. And so let's talk about the framework a little bit. The framework has individual chapters dedicated to each of the standards, each of the 3 dimensions of science instruction. In Chapter 3, it describes the science and engineering practices. In Chapter 4, it describes the cross-cutting concepts. And Chapters 5, 6, and 7 describe the disciplinary core ideas in physical, life, and earth and space sciences. If you want to understand the new science standards, it might be a good idea to become familiar with the framework. You don't need to read it cover to cover, but definitely become familiar with the aspects of these 3 dimensions. And so let's break it down a little bit further. What really is 3-dimensional science instruction? So if we take a look, this is what we call the bare bones review of 3D instruction. The first dimension is what we call the science and engineering practices. They describe the behaviors that scientists engage in as they investigate and build models and theories about the natural world. They're a key set of engineering practices also that engineers use as they design and build models and systems. The framework uses the term practices instead of a term like skills to emphasize that engaging in scientific investigation requires not only skill, but also knowledge that is specific to each practice. There are 8 science and engineering practices. One example is that students are asked to develop and use models. The models they make will help develop explanations about natural phenomena. Models make it possible to go beyond what can be observed and enables the students to make predictions in order to test hypothetical explanations. The second dimension is called the cross-cutting concepts, and they are taught in the context of instruction within the core ideas and not in isolation. There are 7 cross-cutting concepts, and they deal with issues regarding patterns, for example. One example we can discuss is like in middle school students discuss patterns both on the micro and macroscopic levels, and high school students can understand patterns that vary in a system depending on the scale at which the system is studied. In engineering, patterns of system failure may lead to design improvements. So assisting children with pattern recognition facilitates learning, which causes the brain to search for meaning in real-world context. And the final dimension, or third dimension, is what we call the core ideas. This is the dimension that describes the most important aspects of science: the physical sciences, earth and space sciences, life sciences, and science and engineering in the everyday world. The core ideas are used to build a coherent progression of learning for students from kindergarten through 12th grade. And so, what I thought would be helpful in order to really deepen your understanding of 3-dimensional science instruction is to watch this video. And just a quick disclaimer is that this is a video that was made for the Next Generation Science Standards, but because we have also the 3 dimensions in our Arizona Science Standards, this video can be applied to our standards as well. So if you hear the term NGSS in the video, please just replace it in your mind with Arizona Science Standards. And after we watch the video, it's about 6 minutes long. We're going to have a little collaboration in the chat regarding these 3 questions. Go ahead and just read over these questions quickly, and I will prepare the video.
Okay.
It's 1.2.
When we learn things, it isn't for memorizing a piece of information. Just reciting science facts or principles is not what we want children to be able to do. We want them to be able to go out in the world and make sense of novel phenomena. So making sense of things really is engaging in a performance and saying, I need to construct an explanation of why or how this occurs. Okay, let's get started.
Are you ready?
56.
Throughout the 2 days, I want you to engage as the scientist, you as the student, you as the learner.
If it was room temperature water, would it be behaving in the same way?
What's the science behind this? What's happening? As teachers start focusing on the next generation science standards, they will be able to help students see science as it really is, that it's not just a set of steps and procedures.
The real hope is that they can make a connection between what we do in the modeling of performances of science and what they do in their classroom.
Oh, wow.
In this day and age, one of the factors influencing the next generation science standards is the globalization, understanding we're in a global community. We're not kind of an isolated entity here.
The next generation science standards takes the vision from the framework for K-12 science education and puts it into a set of performance expectations. And it calls for the students to actively engage in science. It sets out parameters for science education, clear goals, along with describing the 3 dimensions that students can engage in to make sense of science. 3 dimensions are the cross-cutting concepts, the science and engineering practices, and the disciplinary core ideas.
Most of those ideas are not new. The integration of them, pulling those 3 dimensions together, is new.
If we're going to have the kids doing that, instruction has to reflect that.
What I'm walking away from today, kind of a big shift for me, is we can focus in on something very specific to help teach a much broader, bigger idea, that it actually helps the students be able to do that application to new scenarios, new situations.
Cross-cutting concepts. There's 7 of them. The way we've organized them is around causality, structure and function, systems, scale and proportion, change and stability, matter and energy, and then the last thing, patterns. These cross-cutting concepts are tools that you provide to the children, and they use those tools to make sense of phenomena.
So we're looking for changes in the system.
There's condensation on the outside.
The cross-cutting concepts are a way of organizing the phenomena in terms of what the system is that's being studied. What did you define as your system?
We included in our system also the surrounding air.
The idea that there's a cause-effect relationship.
What's causing the cloudiness?
That's causing the bubbles to come off of the ice.
It's going to get pushed in the direction of the wind, right?
And finally, patterns used as evidence to support their explanations.
So to me, the pattern is just the fluttering back and forth, right? Do you have a question in mind?
Why that pattern, that
The back and forth
pattern?
What if we change the direction of the flag, if we turn it this way?
Okay. I want to go inside and make a little paper flag that we can blow on and manipulate.
The practices are a set of things that children do in engaging in science performances. Asking questions right here, that's what students do. As a professional teacher, you have to create an environment in which students are asking questions that help them make sense of things.
Ready?
150.
Why doesn't that ball return to that exact same level that you dropped it? Engaging students in the practices really does pique their curiosity, and it helps them have a desire to go out and have more questions about the world, which asking questions is a practice. So it's something we want them to be able to do, to be able to discover more about the world. What else contributes to it not reaching its maximum height that it started at?
The pull of gravity. Gravity is still pulling it back down even though it's bouncing up. As learners, using evidence and using that evidence to construct explanations is important. I think having those experiences will really help students own the content.
More bounce, more energy in the bounce, and that's really the kinetic energy.
The last dimension of the core ideas, and there's nothing new here. We don't want kids at the end of instruction to recite the core ideas. We want them to use them in science performances to make sense of novel phenomena, applying them to construct explanations, and develop arguments.
So the alcohol is less dense than the ice. You can see the density in there is different.
Oh, yeah.
The core ideas in particular become valuable because we revisit them through every grade band, and they're moving forward in a very logical way. Those things we're asking them to do can be applied to more than just alcohol and water. It can be applied to cloud formation. It can be applied to condensation.
Why? What's happening? I think what's exciting about the next generation science standards is this intersection of the three dimensions, and that we're not just working on practices one day. You really are infusing the three dimensions within the classroom.
One of the things that you've done is asking what if. By doing that, I have to be able to take what I know, what I've learned, looking at the models, looking at patterns, and applying them somehow to show that I understand what would happen if I changed a dynamic.
It's been real helpful to remember that, I can't do one without thinking about the other.
No change, we should add that, right?
That's how students are going to be thinking about them as well.
It's cute.
It's my hope that this will be the reform in science education that not only gets students more proficient in science, but builds interest in science.
Yeah, definitely, Angela. Thank you. Can't do one without thinking about the other. Excellent. They definitely work together. Thank you for that. All right, so I hope you have a good foundational knowledge of the three dimensions, and we're going to dive into them a little bit deeper here in just a second. If you still have an idea to share, go ahead and feel free to put it in the chat. So we just had our opportunity to share, and let's dive into the three dimensions. So the first dimension is what we call the science and engineering practices. This really isn't that new. If you think of the old strands where kids were, using their process skills like observing, communicating, we're still doing that. We're just calling them practices because we want our students to be engaging in these over and over again. Practice means that it's an iterative process that we engage in over and over again. So there are 8 of these, and this is what we call Dimension 1, what we do. This is what the students are doing. And so if you look at number 1 and 6, the reason that these are color-coded in this fashion is because it's really kind of a 2-part practice. The yellow pertains to what scientists do, and the green is for what engineers do. So scientists ask questions, engineers define problems. And for number 6, scientists construct explanations, and engineers design solutions. It doesn't mean that the rest of these are not important. It just means everything that's in white is what scientists do, and we're just really calling out the difference in number 1 and number 6 between scientists and engineers. And so what's really exciting about these science and engineering practices is that when you have your students engage in one of these, for example, if I ask my students to construct an explanation or design a solution, I'm not just doing this in isolation. Think about if you asked your students to construct an explanation. In order to do that, I bet they had to collect some evidence and engage in argument using that evidence. And in order to collect evidence, I bet they were obtaining and communicating information and evaluating it. So when we think of these practices, they are not in isolation. When we engage in one of the practices, we most likely are engaging in more than one. And there's this interconnectivity that exists, and it's a really beautiful thing to watch. And so let's move on to Dimension 2, which is how we think about phenomena in our real world. So the cross-cutting concepts, there are 7 of them. The numbers are arbitrary. They don't mean 1 is better than 6, or they're not hierarchical in any way. It just means there are 7 of them. And this is really the lens through which students think about phenomena. And so it doesn't mean that I'm going to come out one day and say, hey students, today we're going to learn about patterns. No, after we engage in some learning opportunities and we engage in phenomena, we're trying to explain it, we may look for patterns to help us explain that phenomena, or we might look at energy and matter to help us explain that phenomena. For example, if I were to engage my students in learning about weather, could I engage them in looking at patterns, weather patterns? Or could I decide to look through the lens of cause and effect, scale, proportion, and quantity, systems and system models? Could we think of the lens of how energy and matter cycle throughout our planet? Could we think of the structure and function and stability and change? So the really beautiful thing about the cross-cutting concepts is that you can really choose the lens you really want to focus on when you're engaging your students in discussion around explaining natural phenomena. And so the third dimension, we have what's called the core ideas for knowing science and the core ideas for using science. We broke our third dimension into two separate parts, and I'll explain why in a minute. So right here, this is nothing new. Our students are always going to need content knowledge around physical science, earth and space science, and life science. That has not changed. We are just calling these the core ideas of knowing science, which is what the students need to learn. There are 10 core ideas listed here. In addition to these core ideas for knowing science, we also have what's called the core ideas for using science, and this really relates to nature of science. How do we make sense of phenomena through investigations and observations? How do we engage in the engineering design process to solve problems or create products? And applications of science in the real world. So if you look at this slide, we have 3 core ideas. They're identified as U1, U2, and U3. U1, whenever you see a U1 represented in our standards, this is a sense-making standard. This is when students are doing the hands-on investigations, engaging in discussion, constructing explanations, and using evidence to argue from. If you see a U2 embedded in the standard, that means the students will be engaging in the engineering design process and trying to solve problems or create a product. If you see U3 represented in our standard, this is where we discuss the applications of science in society, or the positive and negative ethical, social, economic, and political implications. So here we go. This is a really great document that I will provide for you in my follow-up email when we're finished. This is called our Arizona Science Standards Framework Snapshot, and it describes our 3 dimensions in one really nice format. As an educator, I suggest taking this out whenever you're planning a lesson or a learning sequence, and really just sitting down to make sure that you have incorporated all 3 dimensions in your learning sequence. So the first dimension are the science and engineering practices. This is what students are doing. The second is the cross-cutting concepts. This is how students are thinking about phenomena. Third dimension includes both the core ideas of knowing and the core ideas of using science. So together, they make our 3 dimensions for our new Arizona Science Standards. And so let's break it down. This is going to help us understand what does the coding of the standards mean and how do we break it down. So I picked 2 standards. I picked one from kindergarten and one from 2nd grade. And if you look, the first number or letter defines the grade level. So we have kindergarten and 2nd grade. The second portion, E1U1, that describes the core idea or the content of science the students are going to know and use. Finally, the last number is an arbitrary number. It does not mean anything other than for identification purposes. For example, the one on the top is Kindergarten Earth Science Standard 3. The bottom one is 2nd grade Earth Science Standard number 4. And so let's break it down even further using the snapshot. So we're going to break down the 2nd grade standard. 2 obviously means grade 2. E1, if you come and look at where the arrow is going, E1 describes the Earth Science Standard for knowing. U1 describes what the students will be using science. So this is our sense making, investigating, developing models, making sense of phenomena. The majority of Arizona's new standards fall in the U1 category. And so, if you have not seen the standards document yet, this is what it looks like. And I will provide a copy of all the standards for you in our follow-up email. And so let's break it down a little more. If you look at this document online, you will see the blue writing. Obviously, if you print it off, it may be black. But the science and engineering practice is at the very beginning of every single standard, and it is bolded and underlined and very easily identified. So if we look at the top example, it says develop and use a model. So this is 4th grade. I can clearly see the science and engineering practice called out right at the beginning. The core idea is underlined here in the orangish yellow color, and that describes what the students need to know. The cross-cutting concept is not easily identifiable, but if you read it, I can see the word system and I can see energy. So there's actually 2 cross-cutting concepts I can choose from in order to decide which lens do I want my students to engage and think about phenomena. And on the right, if you look on the side, there's this very long paragraph. And inside that paragraph, first of all, this paragraph is not what you are supposed to teach the students. This is background information that is pulled directly from the research document, the framework, or the big ideas that describes what background knowledge was used to develop those standards. So if you look at the black circles and you see an in-text citation with the number 4, that means that that information came verbatim from the Framework for Science Education. If you see in a different standard the number 2 written as an in-text citation, that means it came from the other research document working with big ideas of science education. And so let's put it all together and really see if our standards are 3-dimensional. So we'll take a look at this 4th grade standard. So do we see the science and engineering practice embedded? This is what students are doing. It's developing using models written right at the beginning of the standard. How are our students thinking is the cross-cutting concept. We can choose either energy and matter or systems and system models. It is up to us to decide. And finally, what are the students learning? That's the core idea, and this is P4, which describes energy and what the students need to know about it. So that is how you break down a standard to make sure that you are hitting all 3 dimensions. So let's take a look at high school. High school has what we call essential standards and plus standards, and I'll talk to you about that a little more in the next slide. But just so you can get a visual of what this actually looks like, here is what essential standards look like in the document. The plus standards are written beneath it. Essential standards are the ones that can be assessed on the state of science assessment. So the essential standards is intended for every student to have learned by the end of 3 credits of high school science. And the goal is to prepare students for adult science literacy. So essential standards are exactly that. They're essential for every student in high school to have. The plus standards are in addition to the essential standards. They are supporting standards designed to be used with an essential standard, and they're for students taking a more specific course in physics, chemistry, biology, etc., and prepares them for college-level courses. They may be assessed by districts, but they will not be assessed by the state. And so I thought it would be fun for us to give it a try. So I've pulled out 3 different examples of standards, one from kindergarten through 2nd grade, one from 6th through 8, and one from high school. And what I'd like us to try to do is to see if you can read a standard. So pick one. Do you want to do K2, 6, 8, or high school? And see if you can identify, 1, the science and engineering practice, what is the core idea, and what is the cross-cutting concept. And if you wouldn't mind collaborating in the chat box, that would be great to see if you can pull these 3 dimensions out of the standard you chose. All right, we'll move on. If you still want to type, that's okay. Thank you, Martha. So in the first example, the science and engineering practice is plan and carry out investigations. In 6-8, analyze and interpret data. And in high school, analyze and interpret data. So I hope you realize this is already embedded in our standard and is at the very beginning of every standard. The core idea, P1, which is physical science, and there's the language that is attached to that. In 6th grade, this is also P1 or physical science, and P1 in high school as well. So the cross-cutting concept for K2 is cause and effect, and I thought about that because I saw the word cause sitting there where it says, or cooling can cause a phase change. So when I see the word cause, I automatically thought cause and effect. For 6th grade, or 6th through 8th, I thought about cause and effect, energy and matter, or patterns, depending on which lens I really want my students to think about the phenomena. I could choose any of those. And high school, I thought about cause and effect when reading this, stability and change, because I think of gas logs being, the way they react to things is unstable. Or system and system models. How do, gas molecules interact in a system? So again, the cross-cutting concepts are the lens through which we really want our students to think about the phenomena. And so we are almost done, and I actually finished earlier than I normally do, which means we can have that conversation about standard. If you have any questions, I did want to leave some time for that, so we can spend a minute or two on questions, and then I do have one more thing to show you if you're interested. So does anyone have any questions? When we think about the old standards, it's not, how should I frame this? The new standards have a lot of things in common with the old standards. So it's not like you're scrapping everything you've ever done. Physical science is still physical science. Earth and space is still earth and space. What you can start doing fairly easily to implement the new standards is start with the science and engineering practices. Can I teach my students how to engage in developing and using a model through diagramming and describing what's happening on paper and having them explain it? Can I have them doing claims, evidence, and reasoning, which is the CER? Can I use that to help my students construct explanations? Can I engage my students in asking questions? Those are the things that are really easy to transition to because you're most likely doing many of those things. You may have just done them in isolation using the performance objectives, where now we're embedding them. So if I'm going to teach something in regards to weather, I can engage my students in the practices, still teaching the content I have. Hopefully the content matches up in your grade level. But if I were in your shoes, where would I start? I would start with engaging my students in with phenomena. If you're not sure about phenomena, I'm going to do a webinar on phenomena coming up soon. Check on the EMS. I already booked 3 webinars for that. And phenomena is really just picking an observable event that happens in the natural world that requires some explanation. And so we used to call this the hook or the motivator back in the day. Some people call it the problem, or like the essential question. We're calling it phenomena. We're really going to engage our students in this phenomena at the beginning of our learning, because we want them, instead of learning about something, figuring something out. That's where the shift comes in. We're no longer learning about, we're figuring out. So we call it an anchor phenomena. I really anchor their learning in this one phenomena that's going to help them figure out the science and engage in those practices. And so if I were implementing the new standards from the beginning, I would start with, is there a phenomena that I can find that goes with my content? And what practices can I engage my students in? That's an easy doorway into the new standards. And to really think about who is really going to need to be exposed to the new standards are the students who are going to be in 5th grade in year 3. So if you backtrack, those kids are in grade 3 right now, they're in grade 6, and they're in grade 9. Those are the target grades for this year, absolutely. If you're not in one of those grades, it's not that you shouldn't be doing it, it's just that those kids are going to be the first group or class to take the new assessment in 2 years, as a 5th grader, as an 8th grader, as an 11th grader. So really, if you want to do some learning about the practices, I suggest going, I'll type it in here, go to Bozeman Science. They have videos on every single science and engineering practice, and I have used them many, many, many times in PD, and they're really, really great. And they have them for the cross-cutting concepts as well. If you have any more questions, I'm happy to explain it. So yeah, I would teach the new standards because the best part about the new standards is the DOK level that we're reaching using these new standards. Even if they take the AIM Science, your kids are going to be amazing because they're critical thinkers, and anything that's thrown at them from the AIMS, they're going to be able to figure out. Perfect. Awesome. And so real quick, since we have time, if you guys want to look at the screen, this is a document that's also on our website that explains where the standards fall in each grade level. So if I look across starting at P1 and I go straight across, P1 is not in kindergarten, not in 1st grade, but it shows up in 2nd grade. Then it skips 3rd, 4th, and pops up in 5th. And so this is what we call spiraling, right? It's not going to be everywhere all the time, but the kids need to be exposed at it in the grade level that it's called out in. I hope that makes sense. Does anyone else have any questions? No more questions. Okay, so we finished 5 minutes early. That's amazing. Last time I was over by 10 minutes. So thank you all for being here. Please reach out to me if you have any questions. I'm happy to talk to you on the phone and brainstorm with you, think through things, whatever you need. Here's my contact information, and then please be sure that you fill out that survey, and it will, that way, once you've completed it, you can print your certificate from the EMS. So thank you all for coming, and please reach out if you need anything.